So here we're going to talk about polymorphs. And polymorphs, we can define this term by breaking it apart. So poly means multiple, and morph means form. So we have minerals in this case that take on different forms. What we mean by different forms is they have different crystallographic structures. And we're going to use this nice diagram from Dexter Perkins' online mineralogy textbook to illustrate. So all of the minerals that are shown below have the formula Al2SiO5, so two aluminum atoms, a silicon atom that is always in fourfold coordination, and then oxygens. There's 5 of them per formula unit. But even though kyanite, sillimanite, and andalusite all have the same chemical formula, they're not the same minerals because they have a different crystallographic structure. And one of the ways we can illustrate that is by showing the coordination. So for kyanite, all of the aluminum is in six-fold coordinations. We could write aluminum with a Roman numeral 6 above it, and that would be Al2SiO5. Whereas with sillimanite, however, we're going to separate the two aluminums. We're going to write them twice. So you'll see this in a lot of chemical formulas where an aluminum is written twice. And the reason why is because here it has different coordination numbers. So one aluminum is in six-fold coordination and the other is in four-fold coordination. So we still have Al2SiO5, but writing aluminum twice because those aluminums have different structural sites. And then with andalusite, same kind of issue here. We'll see if we can squeeze it in. We'll have aluminum, again in six-fold coordination, but another aluminum in five-fold coordination, and then silica O5. So they all have the formula Al2SiO5. But the aluminum is occupying different sites. Notice that, or different kinds of sites. Notice that for kyanite, the one that is stable at high pressure, whether we have andalusite or sillimanite, if we increase the pressure, we would cross over into the kyanite stability field, that this has the highest coordination. So that's a general principle. As we moved from, in general, lower to higher pressures, it's not a hard and fast law, but for the most part, cations are going to take on a higher coordination number. Now we could take advantage of this double-paneled figure from Dexter Perkins' textbook to illustrate something else, and that is an issue of stability. So when we talk about polymorphs, well, which ones are going to be stable? Well, we've shown here already, you can see by inspection, kyanite is the high pressure polymorph, sillimanite is the high temperature polymorph, and andalusite is occupying this field down here at lower pressure and lower temperature. We could always also think about the Gibbs free energy. So if we were to compare, let's say, the Gibbs free energy at, let's say, this point here, well, at this point here, we're in the kyanite stability field. So we're a little above 6 kilobars and a little over 400 degrees temperature in degrees centigrade. So what would the Gibbs free energy look like? Well, the Gibbs free energy, if we're going to compare something like, let's say, kyanite to andalusite, the kyanite would be more stable. It would have a lower Gibbs free energy than the andalusite. There might be a little bit of a energy barrier there, an activation energy barrier. So if we had andalusite, it might be metastable, sitting in this relatively low energy well, but it's not the lowest possible energy. And if we were to give it a kick, it should be able to make it over that hump and fall into this lower energy, more stable state of kyanite over here. And so we could play that game for all these panels, comparing the minerals in any which order we like. But basically the bottom line is that if we're in this field here, then sillimanite has the lowest Gibbs free energy. If we're in this yellow field here, then kyanite has the lowest Gibbs free energy. By the same token, in this field here, andalusite has the lowest Gibbs free energy. So that's it for polymorphs. Things that have, these are crystals or minerals that have multiple forms, and the multiple forms that we see in nature are going to be controlled by the Gibbs free energy, what is stable, and they'll be differentiated based on their structure.